So thanks, Emily, for this for a great introduction. This is what Pranav asked me to address today, and there's no way I can do that. If you want to invite me for 6 more lectures, I'd be happy to cover half of it. But this is pretty much, I think, everything that you guys put up on the first slide for the semester. So what I'm going to talk about today are what I hope are more fundamentals rather than some of the technology details. How maybe give you some perspective, or at least one perspective about. All right, so specifically, I'll talk a little bit about the Clinical Informatics Fellowship that you may not be aware of, which is a subspecialty training option for people wanting to specialize in informatics, not just AI. And then I'll conclude with some quantifications. So, okay, there we go. So when people talk about AI, they often talk about just ChatGPT. So I took AI as an undergrad in 1988, and we learned about symbolic AI, which tries to reason about the world with symbols, do things like planning. You know, how do you move a robot around in space? As well as statistical AI, which is what you now think of as AI, where you have basically huge statistical models that associate concepts from that represent something in the real world. And so AI, the term was coined actually in the 1950s at a conference in Dartmouth. And it sort of referred to trying to get the computer to do things that humans were good at, right? So things that you find very easy, for example, if I hand you a cup full of water and ask you to carry it from here to the back of the room, I don't have to tell you to hold the open end up, right? You'll know that. Computers don't. Okay. And so those kinds of common sense things, by the way, as an example from Doug Lenott's work on psych, the famous computer scientist who died last year. I'll talk about him a bit later. In the 1960s, you had machine learning, and that was associated with the Cold War. So the Americans wanted to translate automatically from Russian to English so that they could know what the Ruskies were doing. And so the computer scientists said, we can do that. We can do automated translation. Russian, by the way, is a hard language, so it's hard to train people to understand it. There's a lot of swearing. And so that didn't work out as well as they hoped. And so there was something called the Allport Report in the, I think it was the late 60s, early 70s, which was very critical of the automated translation effort. And you had a sudden drop in funding. The baby went out with the bathwater, and you had the first AI winter. Okay. And then in the 1970s, people said, well, you know, we think the brain works using this network of simple units connected together, and the complexity comes from the number of these units and the number of the connections. They call that neural networks. And if you just build a neural network that's large enough, you can have general intelligence, right? And then you can just exceed human intelligence, and we would have the singularity, and the world would be a better place. So that didn't work out so well. And so in the 1980s, you had the second AI winter. And so you couldn't get your AI projects funded. If you said that you were going to do AI, nobody would give you any money to start a company or to do a grant or whatever. And then in the 2000s, as you know, there was this thing called the internet. You may have heard of it. And particularly the web, which, and by the way, the internet, DARPANET, started out here in the 60s. So the internet precedes the web by a good 20 to 30 years. But the thing about the web is that it encouraged a lot of content, stuff, to be uploaded. Okay, and that meant images, that was text, people's thoughts, and emails, and whatever else. And so a bunch of content came online. And so at the same time, as you know, Moore's law, computational power increases, the cost per unit of computation drops. And so you had a resurgence of this thing called deep learning, which, by the way, is pretty much neural networks. but enabled by a lot more computation and a lot more data. And so that's why when you think about AI, you think about statistical AI, because trying to encode the world, understand the world has become harder than just associating things together. And you can, if you associate things together enough, you get what seems like intelligent behavior. And then generative AI is an outgrowth of that. And I won't go too much into that. All right. So these are just a bunch of gee-whiz curves. And I think my boss, Josh Gang, who's the dean of the School of Biomedical Informatics, he collected a bunch of these. So basically, AI is taking off. Sorry about the fact that this is showing up in a Microsoft Teams window, so a little bit of this obscured. But basically, the healthcare market, the AI in healthcare market, is exploding. If you look at the speed of the AI revolution compared to previous revolutions in human history, the Industrial Revolution, the Agricultural Revolution, is taking place over a much, much shorter time. And so you have much less time to adapt. And so over months and a few years, you have fundamental changes in technology. Go ahead. All right. And so this is a few more gee-whiz slides. So this is on the left side, some sort of test. All right. So this is the score in the USMLE. You might have heard of the USMLE. If you haven't, you will soon. And so it turns out that ChatGPT or GPT-4 probably will do more better than most medical students. Fine. The passing grade on total is 60%, and GPT-4 achieved 90-some%, or at least 86 unprompted. So performance is really good on these standardized tasks. Same thing for dental school. So if you want to get your dental DDS, get your dental boards, I'm not sure how they work, you can use AI as well. I don't think that's a lot better. So where are we and how did we get here? So I mentioned that with the web, a lot of content made it online, so into machine readable form and then available across time and distance. An analogous thing happened in healthcare with the advent of the electronic health record. So back in, let's say 2005, 2006, relatively few patient records as a percentage of all patient records were computerized. Most of it was on paper. And then with government incentives, financial incentives, there was widespread adoption of electronic health records, particularly for large institutions and hospitals. Physician practices lagged behind, and then certification came in, which basically said, look, in order to get credit for having certain functions, this is how we're going to define them, and we're going to rate the products with respect to these functionalities, things like decision support and being able to report certain things and so on. So now, data about patients is now available in machine readable form, not freely available to anybody like cat videos, but still in machine readable form rather than in people's filing cabinets on paper. So there we go. So with electronic health record adoption, you got more machine readable data. You got these electronic health records, institutional electronic health records being aggregated within and across institutions into clinical data warehouses. And not just electronic health record data like notes and labs, but also billing systems and digital radiology and all sorts of other systems. So if you have, that Memorial Hermann is transitioning from Cerner to Epic, but there are dozens, perhaps even hundreds of systems at Memorial Hermann. For example, there's an EEG system that's a separate system from Cerner. There are, I'm sure, a dozen or more other systems that are specialized for various functions at the hospital. So there are lots of systems that we're talking about here. Meanwhile, outside of healthcare, as I mentioned, there's more digital data. There's more processing power that's cheaper. And that allowed us to bring back old ideas, particularly neural networks, right? And we call that deep learning rather than neural networks. And we have generative AIs where these models are able to produce results, generative, that seem to be intelligent. And that's really cool. So that attracted a lot of funding, and both from academia and the industry, and that's a good thing. And if you think about whether or not this will continue, fundamentally, progress in statistical AI depends on three things, which is data, more data, better data, right? More processing power, okay, and cheaper processing power, and more efficient algorithms. And if you look at the graphs of all of those, they're all going up. Okay, so for the foreseeable future, you're going to, you can expect to see AI performance improve over time. When will this end? I don't know. There are lots of threats. It's a philosophical question. So for example, as you have more and more generative AI being implemented and more of the content that's online and available to train AIs is generated by an AI, there are problems that kind of feedback causes. What percentage of online content will be AI generated? How good are people going to be at filtering it out? Those are all questions that I can't address off the top of my head. But at least for the foreseeable future, you're likely to see more and more advances in AI performance. No.
An internet issue.
Maybe it rained outside. Okay, so for that, let's take a step back. So in the 1930s, this guy named Struth did a series of really interesting experiments, which basically showed that humans process meaning. And the way he did that is he showed people words that were congruent and not congruent with how they were shown, the words. So for example, green in a green color versus green in a red color. And he showed that people were much better, much faster at repeating back, let's say, the color, if it was congruent versus not. So in other words, people were not able to separate the meaning from the symbol. Okay? And that's really profound if you think about it. What you process as a human is meaning. That is not what computers do, fundamentally. Fundamentally, computers process electricity on, electricity off. That's it. Okay? And we're leaving out quantum computing for the moment. But what that means is that the complexity of what we see from even the most advanced systems comes from the number of electricity on, electricity off, with no concept of meaning. Okay? So what do these large language models do, or foundation models, if you want to be more precise? So they take an enormous amount of content. So here, I don't know if people can see, it's a map and some sort of visualization of the muscles and bones, some text, the Loch Ness Monster, the Starship Enterprise. They project it into a fundamentally meaningless multidimensional space, make vectors out of it. Okay. And then through some black box that varies on the specific foundation model that you're talking about, it produces answers that, in the words of Doug Lynott, again, the computer scientist that recently died, in his last paper, he wrote that the results produced by these large language models are plausible, but not necessarily correct. Why is that? Because if you think about these models and the way that they compress or encode all of that information that they see is to enable association. So for example, because in the billions and billions and billions of pages that are online, man walks dog occurs more often than dog walks man, when you say blank walks dog, it's going to fill in man. And that is actually how some of these models are trained, fill in the blank, right? So it's going to sound plausible because it's like that which occurs most often in billions and billions of pages. So it's going to present you with results that are going to seem familiar to you by design, whether or not they're true. Okay. So if you think about these systems, they're not actually designed to fool people, but their function is such that they're going to be really good at fooling people. And I already mentioned that the probability of man walks dog is more than dog walks man. These vector spaces are fundamentally not interpretable. You can't sort of open up the black box, look in and say, oh, that's why it recommended this. It's a combination of billions of parameters. And I don't know about you, I can't make sense of billions of parameters and billions of dimensions. In fact, it's quite hard to get a large language model to reliably report confidence. So in other words, you ask it a question, how tall was George Washington? And the model says 6'4". Is it right? I don't know. I don't know how tall George Washington was. But it's much more useful to know how reliable an answer to a question is than just knowing an answer that you have no way to really evaluate. And so one of your former classmates, Akshat Kumar, is working on he's actually written the paper, he's revising the paper, looking at this finding. All right, so I tried some stuff. I wanted to ask, how many people know what pancreatitis is? Inflammation of the pancreas? Excellent, okay. So I asked it whether lox and bagels were good for pancreatitis. Or actually, I think I asked it what's better, lox or bagels, which was a question that I didn't think anybody would think to ask. It's kind of a silly question. And the answer it gave was actually really good. It talked about fat, and it talked about the fact that salmon was a relatively lean food, and bagels contain lots of carbohydrates, and that's pretty good. Like if I asked you a medical student on my service this kind of silly question, and they gave me this answer, I'd be pretty impressed. There are some less positive examples out there in the literature, and some of you may have heard about these. In the interest of time, I won't go over each one of them, but ChatGPT often makes stuff up, particularly references, and they look just like a reference should look. And there are 40 billion citations in Medline. I don't know them all. It's been a while since I graduated med school, and when I graduated med school, I knew each one, of course. There were fewer. There were only like 18,000. Lawyers were sanctioned for using fake cases generated by ChatGPT. And actually, it generates different answers depending on the time. I mentioned the black box, right? This is a commercial service. There's a company that creates a service. They can change it. They don't have to inform you. So I tried some stuff. These examples are from Gina AI, if you want to look it up. These are just questions that I asked it about literature. This is what they did. And so I asked it to write a particular quote. It told me that this is from a particular source. It was wrong. Okay. I told it was wrong. It says, I'm so sorry. You're absolutely right. Thank you so much for correcting me. And then I rephrased the question and gave me the wrong answer again. It doesn't have feelings. It doesn't have shame like a medical student. All right. So sometimes when it's right, it's in doubt, right? So if I asked it a different question, it gave me an answer. It was actually the correct answer. I told it it was wrong. And it said, well, of course you're correct. Thank you so much for correcting me. So again, it's right, it's wrong, gives you an answer. All right. So if you look more in the clinical domain, this was an evaluation of Theatertron in 2022. It's a large foundation model developed in Florida in 2022. And there are a number of standardized tasks. And if you look at the performance on those tasks and you compare it to the performance on those same tasks 11 years earlier without these large language models. 11 years ago, we didn't have these large language models or these foundation models. And you look at the F measure, and you're welcome to the slides, but in the interest of time, just believe me that the performance is similar. So, what's the fundamental challenge? So, in the early 1990s, this guy named Jan van der Leij coined the first law of informatics, and he said that data shall be used only for the purpose for which they were collected. And if there's no purpose, then you shouldn't use the data. Why is that? Because there's context in the data. So the context of a picture from your anatomy book is different than the context of a picture of the Loch Ness Monster or the Starship Enterprise. Okay. One is a work of fiction. One is presumably based in some objective fact, and one is an extrapolation from into the future of some worldview. So that is not encoded in the picture. And so when you try to use data for purposes for which they were not intended, you run into problems. Closer to home, if you think about billing data, which are very ubiquitous in clinical records, so pretty much outside of the VA, a few other locations, every encounter is associated with a set of billing codes. Because believe it or not, when I see a patient at Memorial Hermann wants to get paid and UT wants to get paid, and therefore they insist that I submit these billing codes, and they come after me if I don't. So therefore, almost all medical records and encounters are associated with billing codes. These are collected for billing. We try to use them as if they represent clinical reality. They're not totally different from clinical reality, but they're not the same thing. So just as an example, we looked at, we're trying to find breast cancer in our patients. We just happened to be interested in breast cancer and endometrial cancer for a project. This is a while ago. And if you look at the billing codes, are people familiar with the terms sensitivity and positive predictive value? So sensitive. You guys learn that in medical school, don't you? Yeah. Maybe in second year. So sensitivity is the probability that your test will be positive if the patient has the disease. Think of it that way. Okay. So I'm testing you for COVID, let's say. And let's say you truly have COVID. What is the probability that the test will show that you have COVID? That's sensitivity. Okay. Also known as recall, just a different name. Positive predictive value means if I do a test on you for COVID and it's positive, what is the chance that you actually have COVID? Okay, that's positive predictive value, otherwise known as precision in the computer science literature. And you're going to learn it in the context of diagnostic tests, but it's also useful for computer systems and trying to understand how accurate your retrieval algorithms are. So if you compare, and you have to have some gold standard, you have to know whether your patient has COVID in order to use this. Okay. So in our case, the disease was breast cancer, whether the patient's record reflected that the patient had breast cancer, and the test was our system for retrieval. Okay. System number one was using billing codes. System number two was using all sorts of was a human looking at the chart. We actually did this in the context of our project where we used some natural language processing and fanciness to do better than the billing codes. So the sensitivity of billing codes for breast cancer is about 50%, which is to say you'll miss half your breast cancer. For endometrial cancer, it was about 27%. So you'll miss about 3/4 of it, right? And it's not because that everybody's committing fraud or billing improperly or doing something wrong. It's because they're not trying to represent the full clinical picture by submitting a billing code. So when I see, I'm an internist, so I see patients in the hospital. When I have a patient with 12 different conditions, I don't bill for each one of them on every encounter. I might pick one or two. And usually, they're not, and hopefully they're the most important, but not necessarily. They're usually true. And so if you look at the positive predictive value, 80 to 90%, right? And again, it's not, if there's not a match, if the patient is billed for a condition that they don't have, there are all sorts of good reasons why that might be true. For example, you thought they might have had the condition, you tested for it, they didn't have it. Okay? It's not fraud, there's no bad intent. It's just that the purpose for which the data was collected are different from what you're trying to use them for. So what are we living through right now? People heard of the Gartner hype cycle? So for those of you that haven't, Gartner is a consulting group, and they came up with this idea that whenever there's some new technology, it's the innovation treasure, there inevitably people get really excited. And so you have this peak of inflated expectations. So this technology, whatever it is, will solve everything, whether it's RNAi or whether it's DNA or AI or new drug or whatever it is, right? And then inevitably, this new technology does not solve everything. And you get, remember I talked about AI winters, plural? So we thought it was going to translate Russian. It didn't do that well enough. Bad technology, okay? And so you have this trough of disillusionment. And then eventually, over time, you got to figure out what is the correct role of this technology in the world. What can it actually do well and what can it not do so well? And so somewhere in the middle between it'll do everything and it does nothing is probably where you have this plateau of productivity. You found the right role for this technology. Where do you think we are with AI right now? We're not at the trough yet.
Oh.
Okay, you have not seen a trough. The peak. But we're probably cresting the peak of inflated expectations, right? So there was a RAND report that just came out, gosh, for the past month or two, showed that 80% of AI projects fail. That's actually more than in their methodology, other IT projects, a large percentage of which also fail. So we're probably cresting that peak. Okay. All right, so I already talked about this in the previous slide. So what's the key challenge to us as informaticians, and I would argue for clinicians in general? It's not whether large language models or generative AI or foundation models or whatever you want to call it, whether they're good or bad, or what is their absolute performance on this task or that task. It's really more analogous to managing people, right? So the question is, how do we use large language models to improve health? In light of all these changing data sources, rapidly changing state of the art, the fact that these are, in some sense, fundamentally a black box. There is a full field of explainable AI that tries to open up that black box in various creative ways. But how do we take this technology, not necessarily make it better? That's for the computer scientists. They're working on that, I assure you. For us, the challenge is how do we make use of it? Whether it's 98% accurate, 99% accurate, or 97% accurate, how do we make productive use of it? How do we find the right place in the world for these approaches, that plateau of productivity, if you will? So what does this all mean for medical students? So this is my advice. Take it or leave it. You invited me to speak. You get my opinion. Don't stress about your specialty choice yet. You're going to have to make that decision, but you'll change your mind many times, especially the first and second years until you hit the wards. Don't worry about it. Try to do your best. Get good grades. Don't stay out too late. Don't wear your seatbelts. But don't worry whether you're going to be a surgeon or an internist or a geriatrician. Don't worry about it. The best advice I've ever gotten about choosing a job is find a position where what you want to do is what's valued. Right? So if you want to do research, don't go into private practice. That's not what's valued. It's not that they don't like it. It's not that they think it's bad. It's just not what they do. Similarly, if all you want to do is see patients, there's nothing wrong with that, but don't go into academics because that's not what's valued. Okay. Think about practice settings, academics versus private practice. And again, get a job where that's valued. Okay. Try before you buy. So try things on for size. That's why I'm saying don't stress about it now until you try it. And try to, if you want to go into academics, do some research, see if you like it. It's not a commitment. It's a commitment to finish the project. Otherwise, you're going to piss off your mentor, and that's bad. But it's not a commitment to devote your life to academics or research or cardiology or whatever you're doing your research in, or informatics, whatever. If you're interested in private practice, do an elective with a private practitioner, and then try to separate. And this can be difficult. Try to separate in your mind whether you enjoyed it or didn't enjoy it because you liked or didn't like your supervisor or their setting or their office furniture from what they do, and that can be tough. But do your best. So so that's my advice for medical students in terms of specialty choice. In terms of AI, regardless of what specialty you choose, regardless of your practice setting, AI will be done to you. Okay, you will have to live with these algorithms in one way or another. What you have to really decide is, do you want to be an AI user? Do you want to be an AI adapter? Or do you want to be a creator? So think about it like your iPhone. Okay, very hard to function in modern life without a smartphone of some sort. It's been done, but it's hard. How many of you don't have a smartphone? No one? Why not, right? How many of you program your iPhone? Yeah, so that would be the creators. None of you are creators, right? All of you are users. How many of you downloaded apps on your iPhone? Everybody, right? So that would be an adapter, right? So you've taken your iPhone and you've adapted it to what you want to do. Maybe it's watch Netflix or whatever it is, right? That's not something Apple has or Google or whoever created your smartphone. That may be something they didn't even anticipate when they developed the device initially, right? There are lots of examples of this, but here you are, you've adapted your device. You didn't create new functionality, but you've kind of pulled together the functionality that exists on your device for you. All right. Similarly for AI, think of it as like a smartphone or any other tool. Do you want to be a tool user? Use ChatGPT to help you write a paper or analyze data. You want to be an adapter, and so you modify an AI application to do something that it couldn't do before. Or do you want to be a tool builder where you develop new AI applications? Where in that spectrum do you want to be? Good. Probably not a great option as I don't know anything about it. I don't want to have anything to do with it because, again, you will be interacting with it in one way or another. You might as well have an active role in how you interact with it. Now, the further down you get, the closer to a creator you want to be, the more training you're going to need, right? Whether it's formal training or informal training, whether it's kind of an apprenticeship model or a classroom. And luckily for all of us at UT particularly, you really have this full spectrum from attending a single lecture, here you are, to doing an MD PhD with a focus in AI, okay, and everything in between, right? So sort of orthogonal to that is the Clinical Informatics Fellowship. So there you can do electives at the school or just with folks doing work with AI or informatics as a medical student, as a resident, as a fellow. You can collaborate on projects as faculty. You can get a certificate, which I think is 5 courses. Correct me if I'm wrong, you guys. I think it's 5 courses from the School of Biomedical Informatics. You can do a clinical informatics scholarly concentration as a medical student, where you take a couple of courses, 1 course actually now, and you guys can correct me if I'm misremembering. I wrote it, so I should remember. And then you do a project, and then you attend seminars where other people present, and you present your own work in the seminars. You can do an MD-MS. I think Pranav was doing that. Or again, you can do an MD PhD. So in everything in between. The Clinical Informatics Fellowship is a little bit of a different beast. And what that is, I'll get back to that in a minute, but let me talk about this. So the School of Biomedical Informatics, again, this is from my boss, the dean. I think it was mentioned, it's the only freestanding school and the largest in the country. we do pretty, there aren't really national and scholarship and research expenditures. We're pretty much up there for the country. So you have a lot of resources to choose from. Academic programs, I've sort of covered that. I just wanted this in your note, in the slides. It's not advanced. Oh, there we go. So we have a number of service corps and research centers. I run this one, which is the big arc that Elmer mentioned. There are various groups focused on AI, digital analytics, genomics, and so sort of across the at the top of the slide, you have on the left side bioinformatics, which tends to focus on the molecular. Oh, went ahead on me. I don't know why. The molecular all the way to the population. So that's sort of biological scale. That's how we divide some of the groups up. Lots of projects, lots of research funding. And then I just wanted to finish by talking a little bit about the clinical informatics specialty. So I think this is review for most of you, but there's this thing called medical school, usually 4 years, sometimes 5, but usually 4. Residency, which trains you to be a practitioner with quote unquote specialty. Okay? And then you may, but you don't necessarily go on to a fellowship where you train in a subspecialty. So I just wanted to get the terminology out there. And if some of these, but not all of these, are governed by the ACGME, the Accreditation Council for Graduate Medical Education. And so you can do a fellowship. Residencies are all ACGME accredited, or they should be, because otherwise you can't sit for your specialty boards. So you do a residency in surgery or internal medicine or whatever, you would never want to go to a residency that loses its accreditation. That's a bad thing. You will need to transfer, because then you can't sit for the boards, which means that you will have a lot of trouble getting any job. Okay. So residencies are pretty much universally ACGME accredited. And when they lose their accreditation, that's a big deal. It's national news. When that happened in Philadelphia, and people had to switch residencies. Fellowships are not all accredited, because remember, you already have your specialty certification. Some fellowships are accredited. So if you want to be board certified in cardiology, you have to do an ACGME accredited subspecialty fellowship in cardiology. Relatively recently, I think 2014 or so, clinical informatics became a board certified ACGME accredited specialty. So some, but not all programs went through ACGME certification. If you go to a program that's not ACGME accredited, you may still have your boards in internal medicine or surgery or OB/GYN or whatever else, but you won't be able to sit for the informatics boards. For a while, there was a grandfathering period, so that's how I got my certification. I didn't have to repeat my fellowship, but that's going away. And I think it's too late for you, because you have to have a license to sit for the boards, right? So you have to be out of your residency. And you have to be, I think you have to be board certified, not just board eligible. So for the first years, you would be eligible for fellowship after your residency. So that would be a minimum of 6 years if you go into a 2-year residency, which I think is the shortest. All right. So unlike other fellowships, clinical informatics accepts applicants from all different specialties. So you can be a cardiologist, you can be an internist, you can be a surgeon, you can be an OB/GYN, and enter a clinical informatics fellowship. You can't, for example, do a surgery residency and a cardiology fellowship. They wouldn't let you. You can't do an internal medicine residency and a cardiothoracic surgery fellowship. Those are different tracks. Informatics, you can. You can be a subspecialist. You can be a specialist in anything you want: pathology, radiology, anything else, and ensure a clinical informatics fellowship. It is a match, much like residency, and it does lead to a board certification. 80% of your time is spent doing informatics. 20% of the time is spent doing clinical work in your specialty or subspecialty. So if you come in as an intern, for example, our first fellow, Jeremy Hill, did a dual residency in pediatrics and pediatric genetics. He is practicing genetics 20% time, and he's in his second year of informatics fellowship. Our second fellow, Jachi Gu, is an internist, so he is a hospitalist on the wards, 20% time, his choice. He wants to do inpatient rather than outpatient, and 80% of his time is spent doing informatics. The reason I said it was sort of orthogonal to the other kinds of training is because it's really not research training. It's not classroom training. It is really a traditional fellowship apprenticeship model, right? They do take classes, but it's really more like the rotations that you have in your third and fourth year of medical school, similar to other fellowship. And it's really a preparation for a clinical informatics fellowship role. So, there you go. It's a joint, our fellowship has been accredited. This is our second year of accreditation. One fellow, 2-year program. Our first fellow started in 2023. Jeremy's graduating this coming July 2025. Already has a job. Great. Our second fellow just recently started. We're about to interview our third fellow. It's a joint program between MD Anderson, Memorial Hermann, and UT, with UT as the lead institution because it has to be affiliated with a medical school. The academic program is at the School of Biomedical Informatics. It's through the Division of General Internal Medicine. But again, you don't have to be an internist. You don't have to be general internist. It just happens to be where we house our program. And importantly, our program is meant to be relatively academics. Fellows are required to do a scholarly project. And I can talk about why that is, but we're running out of time. So this is the sample block diagram. This is on our website, so you can look at it if you're interested. This is the second year. And so this is my last slide, concluding pontifications. So computing generally and AI specifically will continue to affect clinical practice, probably more and more. And so this is regardless of specialty, but probably differently in different specialties, right? So radiology and image interpretation may be different from surgery, may be different from, let's say, primary care. You absolutely don't need to be a programmer. It's not a bad thing if you are, but unless you really want to program, you're going to be a really expensive programmer with an MD, and especially if you're clinically viable. That having been said, the ability to think computationally is really important. And Rice actually has a course on computational thinking. Again, you don't have to program, but you have to understand like how computers work and how to decompose a problem in a way, or present the problem in a way that it can be solved using a computer. So things like loops and branching logic, conditional logic, that kind of stuff is really important. And that will allow you to not just interact with programmers, but also understand what's a good problem to address in a particular way. If you can program, that's a bonus, because that number one makes you a really useful collaborator, allows you to prototype your ideas without having to, work with somebody else. But most of your life should not be spent programming. So that's it. Thank you so much.